Okay, and I'm just double checking that it is streaming and we are live. So this is pretty exciting. We've started a new show called The Vault. This is only episode 2, but it's a very important big episode. We're going to get to talk about what the Trustless Bitcoin Vaults are. We're going to get to talk about what the experiment that happened on Wednesday is. So just really excited. It's a very historic moment. I don't know if people have truly, captured the whole enormity of this historic moment. So I think what's really important to look at here is that 2 months after releasing the white paper for Trustless Bitcoin Vaults, we have Babylon Labs now running on the first ever trustless BTC-backed lending experiment on the Ethereum mainnet. So that's no wrap BTC, no intermediaries. So it's just a pretty big deal. So I'm pretty excited to be able to have both of you guys here to kind of talk about that. I think the structure that we'll have here is David will walk us through what those trustless vaults look like. And then Vitalis, you can maybe tell us a little bit about what the experiment is and how it went down. So go ahead, David. I'll let you take it from here. Let me share my screen so we can look at an actual whiteboard. And then we can go from here. All right, take it away, David.
Cool. Hey, Erik. Thanks for bringing us here. So I'm my side job is a professor. So I see a whiteboard and I get very excited suddenly, and it woke me up even. Okay, all right. Yeah. So maybe I'll start from describing a little bit of what's the goal of what we're trying to achieve here. Describe a little bit about the technological challenges, and then I'll pass it over to Vitalis to explain the proof of concept that we built to validate our system against these challenges, and then talk about experiments. So, all right. So here's the goal. Very simple, actually, which is there's a chain that we all know. It's called Ethereum. Okay. Oh, can people see me? That's strange. Are we using the same link or are we using a different link?
I see you.
But I think, Erik, you need to zoom a little bit.
I'm using the same
I'm
link
over
as you share with me.
Okay, I see. I'm zooming in. There we go. I'm zoomed in now. Go ahead and move out of the way.
Yeah, can you put this? Can you put this Ethereum on the top right side? I think that's where my screen is.
I think when we're using
All
it
right.
with pen.
No. Yeah, here's good. Here's good. All right. So interesting. Now mine disappeared. Okay, so that's strange. So we're not mapping to the right place here. So there's some technological problem here. How do I do this? Okay, you know what I mean?
What color is your cursor, David?
What you see and what I see is different. So I don't know how to deal with this problem.
Do you know what color are? I'm trying to determine which cursor is whose to see what the issue is. It could also be that you need to make sure that you have the right tool selected. If you're drawing, you need to select the pencil tool. If
I have the right.
you're trying to
No, the problem is not the right. The problem is not the writing I wrote properly. The problem is that what I see on my iPad and what you see on the share screen is a different location.
Gotcha.
So we're not matching.
Yes. Okay. I'm trying to see if I can find what you have on the iPad, but I'm not seeing anything else unless you're zoomed in somewhere else.
So there's the option if you click on someone's name, you can follow their actions. So, David, can you try writing something?
Yeah, I'm writing.
Okay. Yeah, we see it right here.
On the top right, on the blue's name, like it will follow their actions.
Okay, cool.
All right. Problem solved.
Problem solved. Okay, so well, before we get to all these difficult technical problems, first we need to figure out how to work the whiteboard. Okay, guys. All right. Okay, so here's a problem we want to solve. Okay, so on Ethereum, there are all kinds of smart contracts running all kinds of interesting protocols. Okay. All right. So example, on Ethereum, there's a lending protocol called Morpho. Just an example, but it's one of the biggest lending protocol on Ethereum. It is run by a smart contract. Okay. So Morpho lending protocol is on Ethereum, running on a smart contract Ethereum. Okay, so that's Ethereum. Now, however, you are a Bitcoiner, all right? So you're a Bitcoiner, okay? So you're a Bitcoiner, and you said, hey, you know what? I want to borrow some, for example, USDC or USDT on Morpho. But all I have is Bitcoin because, that's what I believe in, Bitcoin. So I don't want to give away my Bitcoin, but I wouldn't mind using it as a collateral to borrow some USDC or USDT so I can do interesting things with it that I could not do with my Bitcoin. Okay, but I'm facing a problem nowadays. The problem I'm facing nowadays is that I have to go and bring this Bitcoin and convert it into some kind of wrap asset like CBBTC, WBTC. And all these are going through centralized custodian. And I don't want that because not my keys, not my coin. Okay? So I don't want to do that. So what I do now today I can't do anything. I cannot participate in this Morpho lending protocol. Stuck. And on Bitcoin, there's no Morpho lending protocol. So I'm kind of stuck right now. Okay? So the problem that we're trying to solve is to unstuck this Bitcoiner. Okay? So that he can participate in the lending protocol without converting his Bitcoin into WBTC, CBBTC, or whatever XXBTC. Okay? So that's the problem we're trying to solve. I think it's a very worthwhile problem because on the one hand, lending protocols like Morpho or other smart contracts are thriving ecosystem. Many things going on, growing day by day. On the one hand, the Bitcoins are getting more and more valuable. And therefore, the more valuable it is, the more important it is as a collateral. So this is the problem we're trying to solve. Okay, so how do we solve this problem, or what's the approach? Our approach is that we create this concept called a Bitcoin Vault. Okay. Ooh, there's an error. Okay. All right. So Bitcoin Vault is a fancy term, but technically it's a UTXO. It's a UTXO, and it sits on the Bitcoin chain. Okay. Now the Bitcoiner will deposit the Bitcoin into this UTXO, and in such a way that the Bitcoiner have trustless access to this vault, which means that if it borrows money, if you use the Bitcoin as a collateral to borrow money on Morpho, then it should be able to withdraw money from this vault itself without relying on any third party, provided that it has returned the loan properly on the Morpho's lending protocol. Okay. On the other hand, if the collateral has to be liquidated, then it will also be liquidatable by, say, a liquidator from this vault. And all this is done in a trustless fashion. So that's the goal we're trying to achieve. Now, when I did the experiment, no, I didn't do the experiment. When I tweeted about the experiment on Wednesday, I got a bunch of replies. People say, hey, trustless is a very serious word. Don't use it, use it with care. So let me now, therefore, be very clear to the audience here. What do we really mean when we say trustless? When we say trustless, what I mean is we don't have any additional trust assumption beyond some very, very basic trust assumptions. Now, what are the very basic trust assumptions? First, you trust Bitcoin. Hey, man, you're a Bitcoiner. You better trust Bitcoin. So that's a very basic trust assumption. That's number one. Two is that your trust assumption should not be beyond a normal user on the Morpho lending protocol. Okay? So you are a user. If you are just a user on the lending protocol using, say, ETH as a collateral or USDC as a collateral to borrow money, then you will be essentially, for example, trusting Ethereum, the chain. Okay? Or you'll be trusting some kind of oracle that is used in the lending protocol. So those are basic trust. And we assume that the protocol that we design do not have any additional trust assumption beyond these trust assumptions, Bitcoin and the Morpho lending protocol. Okay, so that's sort of what we mean by trustless. All right. Okay. All right. So now to solve this problem, there are a bunch of challenges that arises, and one is that we have to design this vault scripting in a careful way that we do not introduce additional trust assumption. Okay, so that's number one. Number two is we need to leverage off ZK proof technology, because you basically have to prove to the Bitcoin vault certain state on Ethereum so that you can trustlessly access the Bitcoin vault depending on what state the Morpho lending protocol is in. To have to download the entire Ethereum history to do this is impossible. And so ZK proof is a technology which essentially compress all this information in a very compact way to present to Bitcoin. However, a compact proof is not enough because Bitcoin still needs to understand it. And here comes the biggest challenge, which is verification, okay? Which is verification. How does Bitcoin verify the ZK proof? And that is a very difficult problem because Bitcoin has very limited scripting capability. So unlike, say, another chain like Ethereum, suppose you want to verify a ZK proof on Ethereum, that's relatively easy because you can write the ZK verifier, the zero knowledge verifier, as a smart contract on the Ethereum chain. But Bitcoin doesn't have this capability. And finally, we have to do the integration with Morpho or any smart contract that we want to run the application on, because we need to translate, in some sense, what's happening on the Bitcoin side to information that the Morpho lending protocol understands. So there's a translation, okay? So basically, the system we built is to address all these four challenges. And so you can see that it's actually quite a, you use the word historic. I'm just a very nerdy guy, so I tend to be very conservative in using the word historic. But I would say it is quite a significant set of challenges to have to simultaneously solve. Now, we are, the challenges here is one, how to do the scripting properly. Two, ZK proof. Luckily, ZK proof technology has proving systems have improved a lot over the years. So we can leverage off, for example, technologies such as succinct SP1. However, the verification turns out to be super challenging, and it requires us to use a pretty new technique applied to the Bitcoin verification called Garbo circuit. Garbo circuit to essentially shift most of the verification off-chain. And the integration with Morpho is also quite a challenging thing. So essentially, that's kind of the proof of concept that we built, is to validate whether or not we can actually feasibly meet all these challenges. And so I passed the mic. I want to say I passed the mic to Vitalis. So I'll just virtually pass the mic to Vitalis.
Great. Yeah. This looks very nice. So, yeah, I'm not a professor, so I'm going to use. I don't have a drawing pen, so I'm going to use the
Do you not
shape.
get as excited when you see a whiteboard, Vitalis?
I get excited, but I can only use. Yeah, I only have the
Vitalis'
shapes
shirt
on
is
the.
white though. Your shirt is
Yeah.
white, so I think that sort of reflects the whiteboard. Maybe that's his involvement.
I had to wear it like it's a whiteboard session, white. Okay. Yeah, so I'm going to.
Would you like me to move the screen where you have a complete empty whiteboard now?
Oh, yeah, sure. I will go to a little bit to the bottom. But maybe
Okay.
you should click on my name
I'll just,
to follow me.
yeah, I'll click on you. Yeah, there you go. I'm on you right now.
So, yeah, I'll draw a box. I'll call it. I need to use bigger characters. I will call it Ethereum mainnet. Yeah, so what I want to show, maybe to give a short intro. So I'm going to give a bird's eye view of the experiment, uh, and then like we can start getting in more into details of specific components, depending on what the audience would like to learn more of. And maybe I can give this a nicer background. So this is Ethereum mainnet, and on Ethereum mainnet we have Morpho, get a nice darker background. And on the other side, like as David showed, we have Bitcoin mainnet. And yeah, what we want to do is essentially have a borrower deposit their funds into a vault and receive a loan based on this vault from Morpho. So how can we do it? Of course, in order to borrow from a protocol like Morpho, you also need to have a counterparty, a liquidator, if you have a bad debt. So I'm adding the liquidator party here as well. So yeah, this is our setup. These are essentially, we have the Ethereum mainnet, we have Morpho, we have Bitcoin, and we have like our borrower that wants to borrow using, they hold Bitcoin, they want to borrow using it. And we have a liquidator, which is essentially a party that if the borrower's loan goes under the liquidation threshold, they can liquidate the loan. And so, as David said above, we need essentially to provide a zero knowledge proof of events transpiring on Bitcoin, of events transpiring on Ethereum. For example, the borrower has repaid the loan so they can withdraw, or the liquidator has liquidated the loan so they can withdraw from the vault. So what our setup is missing is some sort of Babylon contracts, a sort of a Babylon middleware that essentially provides the necessary information of what's happening on the Ethereum chain so that it can be used off-chain to unlock the vault. So that's our setup. Let me make it a bit bigger here. And our story begins with the borrower wanting to borrow. And first of all, for the borrower to borrow, they need to communicate with the liquidator in advance and set up the conditions of this borrowing contract. And the conditions of this borrowing contract are enforced through garbled circuits. So what the entities, what the borrower and the liquidator need to do in advance is step number 1, set up a garbled circuit. And a garbled circuit is essentially the system in which challenges can happen. So if each one of those parties makes, either the borrower or the liquidator makes a malicious claim, the other one can use the garbled circuit in order to essentially block this claim. We will get into it a bit more down the road when we have an actual challenge. And the borrower and the liquidator have established the conditions for safety purposes, like if there's someone tries to do something wrong, the other can block it. So the borrower can go to Bitcoin and create a vault, deposit BTC into Trustless Vault. And what will happen is on Bitcoin we will have the borrower's vault. And then the borrower, so I'm going through the experiment flow. So these are actually steps that we followed live on the experiment in order, like, so the transaction hashes and so on are all in David's tweet thread. So we deposited Bitcoin into the Trustless Vault, and when the borrower went to the contract suite, and set like, okay, like I have a vault position backed by vault. I have a vault, I want to create a new position. I want to borrow funds using it. And our contract middleware, what they did was they took this request from the borrower, and they minted an intermediate asset called Vault BTC and borrow. And the final step, and I'll touch base again on these 4 steps just for everyone to have the complete picture, is Morpho showed this, and it gives the borrowed USDC. So that's the flow that we followed into the experiment. But what actually happens underneath? So of course we have the creation of the vault on Bitcoin, and that's a Bitcoin transaction that essentially locks the borrower's Bitcoin into a UTXO that follows the Trustless Bitcoin Vault's script, what David mentioned above. And afterwards, what we do is we go to our middleware contracts, and we say like, okay, like I have created a vault, and this means, and I want to borrow from Morpho for USDC using the Bitcoin that I have inside the vault as collateral. And the intermediate contracts verify these conditions, and they go to the Morpho chain, and they want to borrow. But Morpho does not really understand Bitcoin UTXOs. So what we need to do is we need to have a translation between the contents of the vaults and something that Morpho understands. And what Morpho understands is ERC20 assets. So what our intermediate contracts do is, based on the contents of the vault, they mint an ERC20 asset, which we called Vault BTC. In the experiment, we called it experimental Vault BTC to avoid any confusion. And this ERC20 asset is fungible, like only on paper, but in reality it's only controlled by these intermediate contracts that want to ensure that it represents the contents of the vault. And given that it is an ERC20, and we can have like an oracle that maps its price to native Bitcoin, Morpho can understand the value of the underlying collateral that is locked into the vault, and based on this, it can issue a USDC loan. So this is the flow in which we create a position, and this is and we, during our experiment, we did like our experiment had 3 parts. In all of those parts, the first step of our experiment is showing how it starts by the user creating a position and borrowing a USDC. It's these 5 first steps. So with that in mind, maybe I can go to our first experiment with a little bit of a cleaner board. Experiment 1, repay and liquidator unsuccessful claim. So in the first experiment, after the user has borrowed USDC, and maybe I can clean up a little bit here. After the borrower has borrowed USDC backed by their Bitcoin vault, they go and repay the loan. So it's very nice way to do it. Okay. 6, repay loan. And based on this loan repayment, there's an Ethereum state, like the loan has been repaid. and there's an event that smart contracts emit, like here, an event has been emitted that this loan has been repaid. And what the borrower does is they withdraw. So receive event to use for proof. So based on this event, our borrower constructs a zero knowledge proof. And what this zero knowledge proof attests is that on a finalized Ethereum mainnet block, I have repaid this loan and using and this is the a finalized Ethereum block contains the event that designates that I am the rightful owner of to claim the vault because I have repaid the loan. And we use SP1 underneath the surface to generate this zero knowledge proof. And what the borrower does with this proof is they go on Bitcoin and they submit claim. They submit a claim transaction plus the proof. Yeah. And now this is a challenge-based game. So now they submit the claim and they wait, like will the borrower waits for a time loop, like will someone challenge me or not? And for some reason the liquidator in this case actually wants to challenge. That's the liquidator. We are running it like that's the experiment that we want to run and demonstrate. We want the liquidator to actually challenge someone that is the rightful claimer of the vault. So how the liquidator does that is they construct their own proof that essentially says, hey, this event this proof is invalid. This like it's called like the dispute proof. Like this event that the borrower submitted on Bitcoin, this proof, it is an invalid proof, and they take this their dispute and they submit on Bitcoin a challenge. And based on this challenge data, now there's again a challenge period for, in this case, for the borrower to challenge, to say to the liquidator, hey, like your dispute proof is wrong. So for the borrower to defend their claim. And here's where garbled circuits come from. So the borrower takes the dispute proof of the liquidator and they go to the previous garbled circuit that was set up between them at the beginning of this entire interaction. Remember, this is the main safety feature that we build in so that nobody can maliciously claim. And they take this dispute proof and they input it into the garbled circuit. And this garbled circuit has the property that if the dispute proof is invalid, then it spits out a secret. And this secret can be used to actually block someone's challenge. So the depositor does that. So I have limited space here, but I will try to write it. So then extract secret from garbled circuit using bad proof plus block the challenge. And if I make it,
Yeah, maybe here I will say a few words about to the audience. So this idea of extracting secret to block or to enable certain path on Bitcoin is actually a very long history. Protocols like Lightning and Atomic Swap from 10 years ago, and even our Bitcoin staking protocol that we've launched last year is all based on this notion of extracting secret. And here, the biggest difference is that Garbo circuit, in some sense, allow this to be generalized to essentially any state of proving and disproving. And that's what we are leveraging off here.
yeah, perfect. And that's kind of the first experiment on a high mid level, so to say. So in this case, just to recap, to go up, We have the borrower and the liquidator, and the borrower wants to borrow. The liquidator is a representative of the lending protocol that ensures that they can liquidate loans. And before anything happens, both of them set up the key safety mechanism for essentially blocking each other if they do if they try to maliciously claim from the vault. And yeah, based on that, the borrower deposits into the vault. It submits it into the Ethereum mainnet into the smart contract suite, which leads to a USDC being borrowed. And then when the borrower repays their loan, they have essentially the right, the trustless right to withdraw from the vault because they can prove it that they have repaid the loan, and the vault enforces these conditions. But for some reason, the liquidator wanted to challenge this. We're running an experiment after all. We want to test this path, and the borrower can actually respond to this challenge and actually claim the underlying vault that belongs to them. So that's experiment one. The other two experiments are going to be like I will spend much less time on this. Erik, are we good on time?
We're perfect on time.
So I will spend less time because like they are kind of extensions to the above. So what I will do is I will take this first and I will go back to our setup. So what's the second
Maybe
experiment?
so,
Yeah.
Vitalis, maybe before you go on to talk about the other experiments, I can give a little bit of a context here to this technological, I would say almost breakthrough, because the problem of Bitcoin verification of ZK proof is actually a very long-standing problem. People have been trying to solve this problem for multiple years, and it has always been really difficult because it's hard for you to send a verifier, the ZK verifier, to write it on Bitcoin itself is huge. The ZK verifier, even after a lot of optimization, is about one multiple gigabyte. We're talking about a few hundred Bitcoin blocks here. Okay, and so it's impossible. And so what is being achieved here is essentially to shift all this verification to off-chain using the Gobble circuit. So the Gobble circuit itself is actually quite big. It's not small. It's about 40 gigabyte. However, storing it off-chain is much, much, much cheaper, multiple orders of magnitude cheaper than trying to put it on Bitcoin. And that's essentially what is achieved here in this. And I would say that proudly, I think our system is actually the first system that realizes using this concept of Gobble circuit in Bitcoin verification.
Yeah. Yeah. About the cost versus BitVM2, I think like our previous experiment had about 60k, 16k USD to submit, to actually to play the challenge game, while in this case it was about $125 in fees.
Yeah, in fact, that was one of the motivation why we shifted to BitVM3, because we realized that even the development cost of doing experiments on BitVM2 will 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 break will broke us, and so we shifted to BitVM3.
Yeah, true is it's much more scalable and yep, big. I guess it's due to a shout out to the BTVM Alliance for for the work on the garbage circuits, a library that's continuously like every day becoming faster and more uh, yeah, more production ready. I think like how
Yeah, I
this
think this work
game format.
this work is a really super good example of sort of open source collaboration, because it's really a collaboration between several teams, ourselves, Citria, Alpen Labs, etc., and really a lot of brains go into this technology.
Okay, so any other insights? I will get on into the two remaining experiments. So the second experiment, how is it called? It's essentially the borrower maliciously claims without repaying and successfully challenged. So in this second sub-experiment, what we did, let me clean up a bit here. The borrower doesn't repay, and they're like, okay, I will try my luck. I will try to get the funds from inside the vault. So number 6 is claim with bad proof. And what happens next is the liquidator says, no, you will not challenge. So, but this time the liquidator's challenge is a valid one. So they are actually proving that, hey, this is a bad proof. So the borrower can't actually take the challenge proof and go to the garbled circuit to extract any type of secret of the liquidator. So they can't actually block the claim, block the challenge. And this means that the liquidator's challenge after some time is successful and they block it, claim blocked. This does not mean that the liquidator is getting the contents of the vault. The contents of the vault are not being claimed by anyone. This is essentially a safety mechanism for blocking a claim with a bad proof, and that's it. So the vault still.
So Vitalis, maybe a little bit better terminology on point 8 could be challenge blocked. Maybe we can just call it challenge blocked. I think the liquidator's challenge is blocked, right? Is that right? I think so, right? Oh no, challenge is not blocked. The claim is blocked. Yeah, the claim is blocked. Very good. So this challenge is successful, right? Challenge is successful. Got it.
And yeah, that's the second experiment. Now that if you got the first one, now you're pros, and these are kind of easy. And the third one is liquidator claims successfully claims. So maybe this is another interesting example. It's interesting how we did it, I guess, and how it works in practice. So in this case, what's the main health mechanism of lending protocols is that debts, if they surpass, if a debt becomes under collateralized, then it gets liquidated, and there are these actors, the liquidators, that are incentivized to do so and do so fast. So in this example, what we're dealing with in the liquidation scenario is that the underlying collateral cannot support the loan, and the liquidator wants to liquidate in order to, and they should also be able to get to the underlying vault's contents trustlessly. They should be able to actually execute the liquidation and get the funds from the vault without having to trust anyone. So in this example, there's a liquidation. Maybe I can make it more clear. So on step number 6, there's a liquidation, and the liquidator can now receive an event that 7 loan liquidated. And using this event, the liquidator goes and does exactly the same as the claimer did, or the borrower did on experiment number 1. That's number 8, claim. And I will not go further, we saw how the whole thing goes in the experiment, in the first experiment. But in this experiment, in the third one, the claim goes unchallenged. So we basically didn't want to do the challenge path again because we did it on experiment number 1. So this is more of a happy path case. So how did we make a liquidation happen in a controlled environment. Of course, when we deployed on Morpho, we set up a market, and this market was controlled by us, and we set up a liquidator, not a liquidator, an oracle, which we controlled. So essentially, we just manipulated the oracle price, like in this, for the experiment purposes, in order to show the loan as liquidatable. And yeah, those are the three different experiment scenarios. A little bit about the engineering work that went behind this. Yeah, so this has been about 2 months since the white paper, yeah, and we have actually been working non-stop into this to do the proof concept, to essentially set up these contracts, to set up the integration, set up all of these mechanisms, the Bitcoin transactions required, and very importantly also the prover, which is using SP1 beneath the surface, the garbage circuits, and also this is not like an experiment in which this an experiment that can actually be orchestrated and repeated, like it's a repeatable experiment. So this is not just a one-off. So we built the tooling so that this experiment can be repeated, because at the end of the day we're building a connected system, and our work towards this experiment is our work that is useful, and the first stepping stone in our iterations towards building this and getting this to production.
Awesome. Vitalis, I think I want to ask you a question from the community about the experiment, if that's okay with you.
Yes, please.
So the question we have is, when did the Babylon team first start working on the experiment, and then who came up with the idea of conducting the experiment?
So we started. So we've been working on with the goal of an experiment for the last 1.5 months, but we didn't want to just like have a dummy experiment. We wanted to have an experiment that's supported by like a real substance underneath. And who came with the idea of the experiment? I think it was inspired by the experiment that we did with BitVM2 a few months ago. And both of these experiments, I would say, were inspired by the fact that we have production experience, and we know that nothing. We can't really be sure of anything until we see it working, like on Ethereum and Bitcoin mainnet, on mainnet environments.
Yeah, in
Awesome,
fact, when
thank
we
you.
did the experiment on BitVM2, we actually did it on testnet first. And actually, when we tried to do it on mainnet, there were certain challenges, and we need to go back and actually work with the alliance. In fact, I think there was one developer from an alliance team which improved the system to make it work. So you're right, we have to go to the mainnet before we know. But Vitalis, one thing I want to point out the difference, a very important difference between these two experiments, the BitVM2 experiment and the current experiment. The BitVM2 experiment was really an experiment just on the BitVM2 verification process, which is not a small part, but only a part of the whole system. Whereas this experiment, very big difference, is an end-to-end experiment. It exercises the whole system. And I think that is, in some sense, to me, the beauty of this proof of concept is really an integration of not one thing, but four or five different technologies integrated together. And this POC proved that it actually works.
Yeah, exactly. It's a real thing. At the end of the day, it's a real thing.
All right, thank you both. Here's another question. They say, we've seen the word trustless being used and we can tell it's important. Could you tell us why is trustless important here, and how is it different from what's available now?
Yeah, so I think I mentioned that already, right in the beginning. No? Right? So in the beginning, I defined very clearly what trustless here means. Trustless here basically means that you don't want to go through a third party like WBTC or CBBTC to get the asset, you want to be able to essentially have the same trust assumption as though you were using Morpho natively on Ethereum. I think that's sort of the
Yeah.
gold standard here, right? I mean, people use Morpho or any other lending protocol on Ethereum day in and day out, and that's the trust assumptions they're used to. Just because we're using Bitcoin, we don't want to have any additional trust assumption. So that's number one. Number two is we want it to also have equivalent trust assumption as Bitcoin itself, which people also trust. So I think those two are our pillars. Smart contract Ethereum, number one pillar. Bitcoin itself, another pillar. Both are very secure, proven, long track record. And we just don't want to add additional trust assumption beyond those two.
Thank you, David. The next question I see here is regarding the mainnet experiment that we just shared on Wednesday on X. How does it show trustless BTC lending on Ethereum actually works in practice? They want a very easy recap of the demo, what was exactly tested, and they want, I guess, an easier way of reading the results.
Okay, so what we tested is we went into Morpho mainnet, Morpho on Ethereum mainnet, and we set up a market between this Vault BTC intermediate asset and USDC, real USDC. And what we did is we set up like our contracts that control this intermediate like translation asset that translates the contents of the vaults into penny ERC20 that Morpho can understand. Then, based on the contents of the vaults, we minted this asset and we were able to borrow underlying USDC. So it's the first instance in which mainnet Bitcoin is used as trustless collateral to borrow from a market on a mainnet lending application.
Okay, thank you, Vitalis. Let's see here. I'm going to see what other questions we have. Are Babylon's Bitcoin trustless Bitcoin vaults the same type of vaults commonly mentioned in DeFi?
No. The trustless Bitcoin vault is at the end of the day a UTXO on Bitcoin that defines certain conditions for unlocking it. And based on this UTXO, we have built essentially this ZK verification on Bitcoin with garbled circuits and so on. The vaults commonly referenced in DeFi can have different meanings. For example, in Morpho, you deposit your assets on vaults to earn yield. There is also the vaults standard, the AP, I don't remember which exact number, but yeah, those are different.
Okay, thank you, Vitalis. And here's a question. I guess they're a user who's staked Bitcoin before, because they're saying that there was limitations on the amount of Bitcoin you could stake. Will there be any limitations on the amount that you can lend or borrow whenever this goes live? So I'm guessing they're talking about like minimum amount or maximum amount of Bitcoin that can be, lent or borrowed.
Yeah, so this is not fully defined, but there will certainly be some sort of minimum, because there's some value lower beyond which the underlying infrastructure to support the trustless Bitcoin vaults is not going to the underlying infrastructure is going to be more costly than the vaults contents. So there's a lower limit defined by the technology itself.
Okay. Okay,
So
another question.
just to add to that answer,
go ahead, David.
Just to add to that answer, I think, when we launched Bitcoin staking, we start off with a tight cap limit, if the audience remember, and then we gradually raise that limit as we get the system more exercised in terms of security. I would imagine similar progression will happen with the launch of the vault as well.
Okay. Thank you all for that. It says here, here's another question about the roadmap of when the Volts will go live. It says in the previous roadmap, the Volt testnet said it would be launched maybe Q4 in 2025. But since the roadmap has been changed, they would like to know if there's a new timeline about when the Volt testnet will go live. Will it be much earlier or will it be later?
We're already in Q4, so it can't be earlier, right?
That's perfect. Okay. Let's see. We have a lot of questions about what's expected rewards, and so I think we can skip those
Yeah, but
for
just to
now.
answer the question, our targets remain the same, but yeah, we're pushing our efforts to deliver this ASAP.
Okay, thank you. Um, Here's a question looking ahead. I think we got like maybe 2 or 3 more questions after this one. Looking ahead, how might Babylon Vault evolve with potential Bitcoin soft forks like covenants? And could they enable more complex primitives like BTC options or perpetuals natively?
Yeah, so Vitalis, I'll take that first. So yeah, so I think the beauty of the vote design is it does not compromise on trust property because of the lack of opcodes like Covenant. So therefore, the technology does not depend on any soft forks, and that's super important because as we know from the history of Bitcoin, building a protocol, a technology, assuming certain opcodes is a fool's man errand, I believe. On the other hand, if there is a soft fork like a new opcode and so forth, then more functionalities can be achieved perhaps. And we can leverage off that in the evolution of our technology as well.
Okay, thank you. I'm trying to go through the questions because some of these we already answered through the talks. I see one about BitVM3. How does BitVM3 reduce the computational overhead for vault verifications compared to earlier BitVM versions? And what's the fraud-proof challenge window in practice?
Yeah, so I think we already talked about that, right? That the BitVM3 is basically taking the verification off chain. And
That's
so,
right.
for example, Vitalis mentioned about BitVM2 was the biggest transactions was like costing about $16,000. And actually that number is because of two main reasons. One is that the transactions involved are very big. For example, the disproved transaction was 4 megabyte, which is the entire Bitcoin block, the entire Bitcoin block. Number two, equally important, is that these are so-called non-standard transaction. In non-standard transaction, it's not forwarded in the peer-to-peer Bitcoin network. So you need special delivery, like Marathon has a special delivery that we use actually in the experiment called Mara something. I forgot the name now actually, which actually you have to pay special additional price to actually get that block through. That's why it costs so much. With Garbo circuit, everything is taken off chain. Everything is taken off chain, and the on-chain cost is much, much lower. We're talking about less than in the experiment was about 125 bucks. So we're talking about what, 2 orders of magnitude smaller.
All right, thank you, David. So I want to thank both of you guys for actually, being able to walk us through the trustless BTC vaults. Vitalis, thank you for walking us through experiments. I know that's hard to be able to dumb it down for the rest of us. So thank you for making it easier for us to digest. I know, David, that in your final tweet you were thanking a few of our collaborating, partners like Morpho, Succinct. So I know Robin. So I definitely know that we want to thank them for making this all possible for us. And just wondering if you guys had any final thoughts, any final words before we close the whiteboard session.
Yeah, also big thank you to the Morpho team for working with us.
Yeah, definitely.
Yeah, I think as a technologist, I would like to sort of give some a bit perspective to this experiment, right? In some sense, this experiment is like building on, as I mentioned, a set of technologies that would not have been possible even a year ago. Think about all the technology that we built on top of, in addition to the new ones that we built. What are the technology? ZKVM, that's a very complex technology that has only been possible in the last 1 or 2 years. BitVM, so there's multiple versions of BitVM, and this is the most recent evolution. We're using the cutting edge evolution. Smart contract technologies like Morpho. So we're really building on so many people's contributions, and as someone said, progress can only be made if you can stand on the shoulders of giants. And really, we're standing on shoulders of giants here to build this technology. Where it is, I think, a breakthrough in the sense that it's putting together a bunch of pieces, adding innovation and solving, I think, pretty real world, very relevant problem. I think that's sort of our contribution here.
Very well said. Yeah, exactly. I want to also invite our community, our audience to, give us a follow, read the white paper if you get a chance, follow us for updates. If you have any questions, you can join our Discord or Telegram, create a ticket, and we'll be happy to answer any questions. So just really thank you guys for your support, being here for all these streams that we do. It's always a lot of fun. And again, thank you, David. Thank you, Vitalis, for joining us. Thank you for the first couple of seconds. Freaked out about the glitching of the whiteboard, but we pulled through. It was really good.
Thank you.
Hey, thanks a lot, Erik. See you next time.
No problem. Until next time, everyone. Bye.